guys to another physical science lesson. I'm your presenter Nico Swartz. Today we'll be looking at stoichiometry. Stoichi what, you may ask? Very simple, we're just looking at quantitative aspects of chemical change. Let's have a closer look on the board what we are supposed to cover for today. We have a couple of concepts to revise. That is the mole. We're looking at molecular mass, molar volume. We're going to talk about concentration, empirical formula, and then percentage yield. And of course, as usual, we're going to look at a couple of calculations on stoichiometry. Let's start off by talking about the mole. Now, what is the mole? No, it's not that cute little rodent that burrows holes in the ground. It is a quantity of measurement. It's actually an SI unit. Let's go have a look at an example. So the mole is defined as the SI unit for the amount of substance. That is the SI unit for the amount of substance. So similar to kilograms, meters per second, the mole is also just an SI unit. Now what exactly is the mole? So 1 mole is the amount of substance having the same number of particles as there are in 12 grams of carbon 12. So the number of mole is calculated as the mass divided by the molar mass. The mass divided by the molar mass. That brings us to what is molar mass. Now molar mass is the mass of 1 mole of a substance measured in grams per mole. Let's quickly have a brief demonstration of this. If you were asked to calculate the molar mass of water, how would we do that? Let's have a look on the board. So water is H2O. If we were asked to calculate this molar mass, it would be the mass of hydrogen on our periodic table is 1. But there are 2 hydrogens in our formula, plus the mass of oxygen on the periodic table is 16. That means the molar mass of water, H2O, is equal to 2 plus 16, 18 grams per mole. And so too you can work out the molar mass of any other compounds by simply using the periodic table. Find the atomic mass and adding that to whatever other elements are in the compound. The next concept we need to revise is molar volume. Now, what is molar volume? According to Avogadro's law, 1 mole of any gas occupies the same volume at the same temperature and pressure. Now, what is that volume? That particular volume is 22.4 cubic decimeters per mole. And this is at standard temperature and pressure. Now what is the standard temperature? That is 273 Kelvin, and the standard pressure is 1 atmospheric pressure, 101.3 kilopascal. So all gases, when you have 1 mole of that particular gas, we know that the volume would always be 22.4 cubic decimeters per mole. So that is known as our molar volume. Let's have a look at the next concept we need to discuss. Concentration. Now, this concentration is not the focus you need to put into your work, but something completely different. It's defined as the amount of solute per liter of solution. Let's have a quick example. If you have to make a juice using a specific concentrate, now I need you to imagine a little bit. I've got a cup of water, and on the other side I've got a big 25-liter of water. If I just enter 1 teaspoon of your concentrate into the cup and 1 teaspoon of concentrate into the 25-liter, how would they taste? All right? The cup would probably be fine to drink, but the 25-liter would just taste like water. So this is how I picture concentration. So between the two scenarios I've created, which do you think is more concentrated? Which one will have the stronger taste? Yes, you are correct. So the cup would have a better taste because it has, although they've got the same amount of concentrate inside, the volume is much smaller. So in that description you can already pick up what is meant by concentration. Let's have a closer look on the board. Concentration is the number of mole. N is therefore the number of mole. That is the mole. And V being the volume. And let's be aware of our SI units, where your volume must be in cubic decimeters. So never forget to look at your units. Those are the concepts we need to cover for this particular chapter. I want you to go and have a quick break, stretch your legs, come back refreshed, because we're going to go into doing a couple of calculations that you need to know for this chapter. See you on the other side. Welcome back, guys. Are you ready? Are you ready for this? Let's have a look at our very first calculation. Come with me to the board. Our question reads, methyl benzoate is a compound used in perfumes. It is found that, here's our very first values. So many grams sample of this methyl benzoate contains 3,758 grams of carbon, and then we've got 0.316 grams of hydrogen and 1,251 grams of oxygen. Our question says, determine the empirical formula for methyl benzoate. Let's go and have a look at that. So let's start off by working out the percentage carbon. Now the percentage carbon will be, we're taking our masses. Let's go back and have a look at what was the mass for carbon. Our complete sample is 5325, and our carbon we see is 3,75. So it will be the 3,75, and that's 3,758 divided by the whole sample size, which is the 5,32, and that also ends with a 5. If we want a percentage, we have to multiply by 100. If we take out our calculators, guys, quickly take out your calculator, you should find that this is 70,573%. If we continue in this manner and we do the same for hydrogen, what is the percentage of hydrogen? So it will be the mass of hydrogen divided by our sample size, 5,325. We're going to multiply that by 100. So how many grams of hydrogen was there? 0,316. And that should give us a percentage of 5,934. Are you starting to see a pattern? Because I am. So if we need to go and calculate the percentage of oxygen in that sample, we will follow the very same steps. Let's have a look. Percentage oxygen is then equal to, how much oxygen is in the sample? 1,251. Of the complete sample, which is the 5,324, sorry, not 24, it has to be 25. And that is multiplied by 100 to get it into a percentage, and we find that that is 23,493%. We're not done yet. We've now got the percentage of each of these elements in our sample. What else do we need to do now? Now we need to go and calculate the number of mole present in our sample for each of these elements. Let's go and do that. Let's stick with carbon for a moment. We want to know the number of mole of carbon. That is, remember, mass over molar mass. Therefore, that is equal to, we worked out that the carbon was 70,573. And we accept that as grams. We then divided by the molar mass of carbon on the periodic table, which is 12. And that gives us the number of mole of carbon as 5,881. Right, and that is just mole. Let's repeat that now. The number of mole for hydrogen. We know what the formula is. I'm not going to repeat it. But we take that percentage that we calculated for hydrogen, which is 5,934. We divide it by the molar mass of hydrogen on the periodic table is 1. Which gives us the exact same answer, 5,934, and now it's mole. We repeat, the number of mole of oxygen is, the percentage we calculated earlier on was 23,493, and we divided by the molar mass of oxygen, which was 16 on the periodic table, and that gives us 1,468 mole. So you see, there's a lot of repetition in what we are doing. What did we do? We started off by calculating the percentage that each of these elements have within our sample. We took that percentage as the mass, and we then calculated the number of moles that each of these elements have. What is our next step? Now we need to go and divide the moles by the smallest number between the three of them. Let's go and do that quickly. So we will then divide all of these numbers by the smallest one, which is this 1,468. So all numbers divided by 1,468, we will find the following. Carbon, our answer will be 4. For hydrogen, our answer will be 4. And obviously, oxygen, it's the same number divided by itself, therefore oxygen will just be 1. And with that, we can see the empirical formula for our compound is C4, H4, and just 1 oxygen. Well done, guys. So that was our first calculation. Perhaps we should try and do a second one. What do you think? I think so. This is lots of fun, man. Let's do this. Let's have a look at a second example. Question 2 reads that iron reacts with sulfur. So we've got iron that reacts with sulfur and it forms iron sulfide. So our balanced equation should look like that. Now for me it's very important to make sure the equation is balanced. If the question does not say a balanced equation, do not assume that it is balanced. Let's go and check that it's balanced. I see 1 iron, there's 1 iron. And then I see 1 sulfur, there's 1 sulfur. Just to double check, I have 2 elements or 2 atoms on this side, on our left-hand side, and I've got 2 different atoms, although it forms a compound, on the right-hand side. What are we supposed to do? It says calculate which of the 2 substances will be used up completely. If 20 grams of iron and 10 grams of sulfur is mixed and heated. We've read through the question, we've checked that the equation is balanced. What are we asking here? We are asked to actually calculate which is the limiting agent. What do we mean by limiting agent? So this is the reactant which prevents the reaction from continuing and continuing. So it gets used up completely, and when it's used up, the reaction actually reaches completion. So let's go and determine which is our limiting agent. And I think just for a little bit extra, let's go and see what is the excess of the other element. Join me on the board. We will start off by calculating the number of mole of each of the elements. And that would be, what was the mass given for the iron? The mass was 20. And for sulfur, 10. So the number of mole is the mass, and this one is for iron, divided by the molar mass. Please let us not memorize these. Use your periodic table. And you will see that the molar mass of iron is 56. Take out our calculator, and we should find that that is equal to 0,3 0.57 mole. If we do the same for our sulfur, so the number of mole of sulfur is equal to its mass, which they gave us as 10. The molar mass of sulfur on the periodic table is 32. That gives us 0.313 mole. Now I quickly want to go back and talk about the mole ratio. So you'll see that 1 mole, according to our equation, 1 mole of iron reacts with 1 mole of sulfur, and it forms 1 mole of iron sulfide. So the mole ratio for that equation is 1:1, and it forms 1. What does that mean? If we look at the mole ratio, you will realize what we just calculated is not a 1:1 ratio. Can you pick up that iron is a little bit more than sulfur? All right. If our mole ratio is 1:1, why is that not showing in our calculation? Because it means that one of them is in excess and the other one is a limiting agent. So from this, we can clearly see that the number of mole of sulfur, so the N of sulfur, is smaller than the number of mole of our iron. What does that mean? It means that sulfur is our limiting agent. So we've now determined which is the limiting agent. But we still have not answered the question. Let's quickly see again. What was this question we were supposed to answer? Let's go back. We are supposed to calculate which will be used up completely, and we saw that was sulfur. If 20 grams of iron and 10 grams of sulfur are mixed and heated. So now we've answered the question in the sense that we know which one is the limiting agent. We said it's sulfur. But I think just for interest's sake, let's see by how much will the iron be in excess. So this could be a question that could also be asked. Let's see how do we do that. So number of mole is equal to mass over molar mass. The number of mole we saw 0.313. This is the molar mass of sulfur. But remember, sulfur would stop the reaction at this point. That means there will be some iron left to react. We are trying to determine what mass of iron would be used in this particular case. So we want mass, and we've got the molar mass of iron as 56. Therefore, we should find that 17.5 grams of iron is used in this reaction. So how much will be left? How much is in excess? That is easy. We know the sample was 20, and now 17.5 of the iron reacted. That means we are left with 2.5 grams of iron. I think that's very, very simple and very easy. Please take some time and practice these questions, as you can expect a question like this for an examination. Let's quickly take a break, stretch our legs, have some water, and then we come back to have a look at our third example of an examination question. Welcome back, guys. Trust you had a good stretch and had a fresh glass of water and ready for the next challenge. Let's quickly have a look at what question number 3 presents to us. Magnesium burns in air to form magnesium oxide according to the following balanced equation. Remember, those are the key words. We cannot just assume that the equation is balanced. Let's quickly double check, just to be on the safe side. I see 2 magnesiums, and over here I also see 2 magnesiums. Then I see 2 oxygens and 2 times oxygen. So yes, the equation is definitely balanced. What do we need to go and calculate? If the percentage yield of this reaction is only 80%, calculate the mass of magnesium. That's what we need to go and calculate. We need to find the mass of magnesium that needs to be burnt to produce 30 grams of magnesium oxide. Let's go and have a look at our calculation. We'll start off by calculating the number of mole of our product, which is magnesium oxide, is equal to, that's mass over molar mass, and if we substitute, we will have, they ask specifically for 30 grams of magnesium oxide. The molar mass is 40, that is the oxygen plus the magnesium, that gives me 40, and therefore I have 0.75 mole. Let's go back to our equation. That means that magnesium oxide that is formed is 0.75 mole. Now this is important. The mole ratio says that for every 2 magnesiums, it forms 2 magnesium oxides. Our mole ratio is then 1:1 for those 2. That means we now know that the number of mole for magnesium is equal to 0.75 mole. And what would my reason be here? Mole ratio is 1:1. Very important why your equation needs to be balanced. Now, if the number of mole of magnesium is 0.75, we can go and calculate what is the mass. So the mass is equal to the number of mole multiplied by the molar mass. The little r I'm putting in there is the relative molecular mass, is another name. That is equal to 0.75 multiplied by the relative molecular mass or the molar mass of magnesium is 24. Therefore, the mass is 18 grams. Let's go and interpret. What does all of this mean? It means 18 grams of magnesium will form the 30 grams of magnesium oxide. But there's one little catch we need to look out for, and that is that the percentage yield of this reaction is 80%. Alright, so we need to go and work out 80% of our product, which is 30. So, let's see. 80%, 80 over 100 of our 30, and you will see that gives me 24 grams. That means 18 grams of magnesium actually produces 24 grams of magnesium oxide. And so this is not what we want. We want to know how many grams, let's call it X, of magnesium will form those 30 grams of magnesium oxide. We can just cross multiply and we will see that X, which is the mass of magnesium needed to produce the 30, is 18 multiplied by 30, and that is divided by 24. Therefore, 22.5 grams of magnesium will produce our 80% of magnesium oxide. So, we need to be very careful of these little tricks that are in the question. We were almost tempted to think that we were finished with the answer, forgetting that the percentage yield was only 80%. And from there we can actually go and calculate what is the actual grams, the actual mass of magnesium required to produce the 30 grams of magnesium oxide. Let's quickly recap. What are we supposed to know for this particular chapter? We need to understand the mole and the calculations thereof. Number of mole is mass over molar mass. We did not do this as an example, but it's important to remember concentration is equal to your number of mole over volume. We had a good practice with empirical formula and also calculating the limiting agent. That's all we have time for. Thank you so much for joining. Look forward to seeing you in another lesson. Keep safe and be well.